Alrighty, section 7.2, we're going to get some geometric terminology today, some vocabulary, a new symbol, all kinds of fun stuff. Like I mentioned, it's a quick lesson. It's basically just bombarding you with a bunch of vocabulary so that you understand where we're going to go from this point on. So first things first is the definition of what similar means. We talked about congruency. Question?
What was the name of this whole thing? I'm trying to
Geometry.
Well, not that whole thing.
School?
No.
Life.
Sure. Wait, what is it?
Exploring similar polygons.
Thank you.
Similar polygons. That sounds
Somebody was busy talking and couldn't write down.
I was talking about this and I was getting a pencil out, so I would have not seen it anyway.
All right. We talked about congruency already, and congruency in simplistic terms, same shape, same size. Okay, so everything was identical. All the angles were equal, all the sides were equal, et cetera, et cetera. Now we get into similarity. Similarity in simplistic terms, ignoring this definition for a second, is same shape, different size. Okay? Like model cars. You know, you compare a 57 Chevy to the model of a 57 Chevy. Those are similar figures. Same shape, different size. From a geometric standpoint, we get a fancy definition here that says they're similar if and only if their corresponding angles are congruent and their measures are proportional. Common mistake that people make with this definition is they want to make the angles proportional too, and that doesn't make any sense because the angles have to be congruent because certain things can't be violated. For instance, the angles in a triangle have to always equal 180 degrees. So if you have a small triangle and a big triangle, they can't be proportional because all of a sudden the angles in the triangle won't add up to 180 degrees. What's this if and only if mean? We see that all the time, but what does it mean? Or what does it do for us? Nothing? It makes it a reversible statement. So we talked about definitions being, a good definition is something that is reversible, meaning two polygons are similar if and only if their corresponding angles are congruent and their sides are proportional. Then, if you have two polygons that sides are proportional and their angles are congruent, then they have to be similar. So it works both ways. And we're going to be looking at working with it both ways, starting with similar figures and talking about these two things being true, or starting with the two things being true and proving that the figures are similar. Okay. So new notation. This, whoa, look at that. That was cool. This is our new symbol for similar. It's the tilde off the top of the congruency symbol. It's actually called the tilde, but it means similar.
Like in Spanish. I even told you.
Like niña.
Yeah.
See. Same symbol, different meaning. Niña doesn't mean two similar children.
Wait, can't you just, isn't it the same thing as like the congruent symbol?
No, congruent symbol looks like this.
Well,
It's
I
the thing
mean,
on
no,
top of
like,
the
no, like, I
congruent
mean, like, I know it looks different, but doesn't mean the same thing.
No.
What means similar? What means
Those two triangles are congruent.
Yeah.
So this would be equal to this would be equal to this would be equal to this. And that would, okay, congruent. Similar would be same shape, different size. So this angle would equal this angle would equal this angle would equal this angle. However, the sides would not be congruent, but they would be proportional. Pregunta.
So now we can use angle.
Ooh, maybe.
To prove them similar.
Maybe.
We're gonna have to do similar proofs.
Maybe.
Yeah, we do.
Maybe. So when we talked about congruency at the very beginning, we said if these two triangles are congruent, then all 6 parts are congruent, and we listed all those parts. Now what we're changing here with similarity, the angles are still congruent, like I did here in the diagram. However, we get this stuff for the sides. So notice I set up a ratio for each of the sides. It's a little confusing, but this double bar doesn't mean anything. This is the gazinta bar, and then this is the segment symbol.
Wait, the what?
The gazinta bar.
Just a fraction bar.
2 goes into 3.
Why is it called like a
You've never heard that before? The gazinta bar? Gazinta,
Oh.
right? 3 divided by 2. 2 gazinta 3. It's a gazinta bar.
Oh my gosh.
It's not.
Yeah, it is.
Wait, goes into. Oh.
Gazinta.
I get it. I think.
G-A. It's Latin, it means divided by.
That's not what it is.
Yeah.
What's not?
Alright,
That's not the actual word.
Okay. It's not then, I lied to you.
I'm looking
I
it up.
know.
I'm a liar. My pants are on fire.
I hope he's not lying.
Would I lie to you, Nick?
You would
All right, so we got a new symbol now, and we have this. And the common mistake, like I said, that people make is they want to make the angles proportional, or they forget that the sides are proportional. They want to make the sides congruent. If the sides are congruent and the angles are congruent, then we're talking about congruent figures. If the angles are congruent and the sides are proportional, then we're talking about similar figures. Senor?
So what does the tilde mean?
Similar. Yeah. The tilde means this figure is the same shape but different size to this figure.
It's slang math.
So now we get to golden retrievers and dogs again. Are congruent triangles similar?
Yeah.
Yeah.
Are similar triangles congruent?
No.
Not necessarily. Good. Okay. Squeaky shoes today. Scale factor. Next big term. Scale factor is the ratio between the two figures. So if you're building a model car of a 57 Chevy and it's a 1/13th scale, that would be your scale factor. How much smaller or bigger is the thing that you're dealing with? The second term is kind of important here. Depending on which one comes first will determine what your ratio is. Is it in a scale of 3 to 1 or is it in a scale of 1 to 3? You're going to want to ask yourself, did I start with a smaller figure and it got bigger, or I started with a big figure and it got smaller? Just because I'm old, I will sometimes use the phrase ratio of similitude. It's the same thing as a scale factor. It's just an old, and I didn't make that one up.
So you
didn't
did make up.
Gazinta either.
No, I didn't make up Gazinta.
It's online.
Hence the reason I didn't make it up.
You make it sound like you are.
What?
You're using your sarcasm.
Sarcasm? Yeah, like I use sarcasm.
Never mind.
Did you get that? That was a joke. That was called irony. Okay, good. So this is the same thing as this, and sometimes I'll forget and use the other phrase, but just so you know what we're talking about. How much bigger or smaller is that object than the thing that you started with? Okay. 2 triangles, a dog and a cat. Is the triangle dog similar to the triangle cat? Equal up. Were you going to tell us anything? Or, okay, all right.
Yeah.
Oh, I'm sorry. Yeah, as in you were answering the question, not yeah, you're going to tell us something.
Yeah.
Okay, they are? How do you know?
Because the corresponding angles are congruent.
They are? How big is this angle?
70.
How do you know? No. You're using the information that you're trying to prove then that you're trying to prove that information that you're using. Grace.
Because all the angles add up and equal 180.
68 plus 42 from 180 gives us that being 70. Oh, look, it matches that one over there. How big is this angle?
68.
Why?
Because they all add up to 180.
Right, not because that's 68, but because 70 plus 42 from 180 tells me that that's 68. That takes care of half of the issue. We've established now that the 3 angles sorry, the 6 angles are congruent, or the pairs of angles are congruent. What about the sides? Max?
Yeah, because 6 to 2 and is 3 to 1, and 12 to 4 is 3 to 1, and 7.5 to 2.5 is 3 to 1, so they're all proportional.
Are those equal? Well, they all reduce to 3. If you can't reduce them for some reason, then put them into your calculator and reduce the ratios. Put them into a decimal form. But yes, in fact, they're all equal to 3. That takes care of the second requirement. Sides are proportional. Angles are congruent. Yep, they are similar. And then from the last slide, we want to ask ourselves, which one do we start with? Did we start with the yellow and get the blue, Gesundheit, or did we start with the blue and get the yellow? And we need to explore some more terminology for that so that we have common vocabulary to discuss that exact issue. What's the scale factor, by the way?
The ratio of
Which in this problem is what?
3 to 1.
3 to 1, or
1 to 3.
1 to 3, depending on how, because Max chose to write it as 6 over 2. I could have also written it as 2 over 6. So we don't necessarily know which one we started with. So in this case, either answer would be acceptable, 3 to 1 or 1 to 3. Put 3 to 1 up there. Okay. The thing to remember now about not only triangles, but any polygon, if they're similar, then anything that you could measure with a ruler is going to be in that same scale factor. So we're talking about sides of the figure, but we could also talk about altitudes, we could talk about medians, we could talk about perimeters. What am I forgetting? Altitudes, perimeters, medians.
Perpendicular bisector.
Yeah, but we don't really measure the perpendicular bisectors lengthwise. But we could, I mean, if you wanted to, a certain part of it. So again, as I said, I think I have it in here. Yeah, so anything you measure with a ruler will fall under the same scale factor. Area does not. You can't measure area with a ruler. You got to calculate it. That gets into a whole new world of hurt that we're going to get to later. All right, this one is bombarded with information. So the first one is a dilation. Where have you heard that term before?
Eyes.
Yeah, your eyes dilate. Your pupils dilate. They get bigger or smaller depending on whether you're exposed to light or in darkness. So dilation is a type of transformation. It makes something bigger or it makes it smaller. And so we'll use the term reduces or enlarges, meaning make it smaller or make it bigger. Second sentence says if things are similar, then they're going to be dilations of each other. And the third one is the most important part. That's got the two terms that we're going to use a lot. And those terms are pre-image and image. Pre-image is what you start with. Image is what you end with. Going back to the dog and cat example, we have no idea which one the image and which one the pre-image is. So it's usually some information that's given in the problem. And once you know which one the pre-image is, then you can determine what the scale factor is. Is it 3 to 1? Is it 1 to 3? If you don't know which one is the pre-image or the image, then either answer is acceptable. This is not a tried and true rule, but a lot of times when you list a similarity statement, triangle ABC is similar to triangle XYZ. It's commonly implied that this is the pre-image, so we're going from there to there, but I don't always hold true to that rule. So there'll have to be some other information in the problem. And if there isn't, then you can figure that either one of them is the pre-image. Okey-doke. Squeak, 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 squeak. We're going to be doing some dilations on coordinate planes. They're real easy. If I know the coordinates of the coordinates of the three vertices of a triangle and I want to dilate that triangle, either make it bigger or smaller, the process is real simple. You just multiply all the coordinates by the scale factor. So if I have the coordinates of a triangle, which I have an example here, I have the coordinates of a triangle TAR, and I want to enlarge it by a scale factor of 2, I literally go through to all the coordinates and just multiply them by 2, and I'm done. What's more important is this notation. This is what's called prime notation, and so I would read this as triangle TAR is dilated to the triangle T prime, A prime, R prime. So T prime is the dilation or the transformation of the point T. If I take the point T prime and I dilate it, it goes to T double prime, to T triple prime, etc., etc. So where would T prime be? Carter. 2, 6, that's it. Just multiply it by the scale factor. A would be at 14, 0, and R would be at, what are we doing, 2? Yeah, 8, 12. Graphically, it looks like this. So here's my original triangle in blue. And when I dilate it, it gets bigger. When you graph those 3 coordinates, you see that those triangles are similar. The angle measures would be the same, the size would be proportional. Yes, sir?
Are they always going to be overlapping?
No. Because notice if I change my scale factor to something stupid like 1,000, it's going to shoot way over. Yeah. And it would be real big and honking.
Cool.
I have a little video for you.
Can you go back a couple slides?
Sure, what would you like to go back to?
Linear measurements.
Linear measurements. That one? Okay. Okay. Get some audio.
Is this like a math video or
No.
just like a random
This is
video?
a math
Really
video.
think it's a moose video.
I
Oh, I never thought of
would've
that.
put a
This video
math
would
in.
rock. This is a treadmill video.
Oh what?
Treadmill video.
Uh-oh.
Here we go.
Oh boy. I don't know why I'm not getting any sound.
And
This is a good
I don't
start.
want to watch
I don't want to
it.
watch it if there's no sound.
This is a good start. Oh, you still have to change.
Takes the gold off. Look at that. Look at this guy laughing. Yeah, that's all.
Terrible.
Hey!
Great.
You want to watch the cool trick?